Hello and welcome to Keeping Secrets with Field Level Encryption. My name is David Nault. I work on the SDK and connectors team at Couchbase. So today we're going to start with a high-level look at some of the components in the Couchbase Field Level Encryption framework as it's implemented in Java SDK. Then we'll look at a fun little example that uses encryption. We'll talk about how to plug in your own encryption code in case you have special requirements. Then we'll talk about key rotation, what it is, why it's important, and how to do it. And then we'll wrap up with a brief look at how to integrate with HashiCorp Vault and the Transit Secret Engine, which provides encryption as a service. All right, so what are the components of this framework? Well, first, let's talk about keys. If we're going to do encryption, we need secrets. And these secrets are called keys. And in the Couchbase framework, a key has two properties. It has an ID, like the name of the key, and then it has a byte array. It holds the key material. Second component is a keyring. This is the thing that provides access to the keys. So if you're storing keys in a certain location, or you need custom code to access the keys, or if you want to implement key rotation, which we'll talk about later, you do that by implementing the keyring interface. There are encryptors, and these are just what they sound like, little bits of logic that know how to encrypt a plain text message and generate a ciphertext, an encryption result. When you make one of these, if you're going to use a key, you pass the key into the constructor, or the name of the key. That's important. You pass the name of the key into the constructor, and then every time the encryptor encrypts the field, it asks the keyring, hey, get me the key with this name, get me the key with this name. And then it also, if it uses a key, it writes that key name into the encryption result so that the decryptor can undo all the hard work of the encryptor. It can look at the encryption result, get the key name, ask the keyring for that key, and then perform the decryption operation. The interface also has this algorithm method. This is for registering the decryptor with the crypto manager. The crypto manager it maintains like a registry of encryptors and decryptors, and this is kind of like the main configuration point. And we'll look at how to configure a crypto manager with encryptors and decryptors coming up in just a moment after this. First, let's look at what the JSON looks like when you encrypt a field. So on the left over here, we've just got a maxim, and then on the right, let's say we want to encrypt this field. What's it going to look like after we do that? On the right, this is what the encrypted version is going to look like. We've done a couple of things. We've changed the field name. We put little encrypted $ in front of it. That's to identify it as an encrypted field. And then we've changed the value of the field. Instead of a string, now it's a JSON object with a couple of properties. The alg property stands for algorithm. That's the encryption algorithm that was used. And then the KID, that's for key ID, the name of the key, encryption key that was used. And then the ciphertext, that's the encrypted version of the message. Let's look at some code. To set this up, one of the most secretive of all professions, you have the magicians, right? And they're very serious about keeping their secrets. And for this demo, what we're going to do is we're going to build a little application for keeping track of all the rabbits that a magician might have to manage. And in particular, we're going to associate a magic word with each rabbit. This is the magic word that the rabbit responds to pop out of the hat. And in order to protect this magic word from falling into the hands of our rival magicians, we're going to encrypt the magic word when we store this in the database. But that's a setup. All right, let's look at the code. Start by looking at a class to model our rabbit. Simple class with a couple of properties here, a name and a magic word. It's immutable here, so we've got a constructor, and you could use Jackson parameter name module, but for this, we're being explicit and annotating the constructor arguments to tell Jackson which JSON properties to the stuff into the constructor, and then a get name, get magic word, and then the toString just prints this out. The rabbit responds to this magic word. So we want to encrypt the magic word property. So I'm going to add an annotation. If I can spell it. Encrypted. And then we're done. No, well, almost. There's some more configuration to do to get the Couchbase SDK to know what to do, or to configure the crypto manager with like the algorithm to use and things like that. But this is really all it takes to, once you've got that other stuff configured, if you just want to encrypt a field, you just slap this annotation on it. And then whenever you do data binding, that's conversion from the Java object to JSON, whenever you do data binding on it, the encryption will automatically happen transparently during the data binding process. It's kind of cool. I'll briefly mention a couple of properties here. You can specify which encryptor you want to use. If you're using multiple encryptors, you can specify here that when you do this field, you want to use a certain encryptor. There's also the concept of a default encryptor, which is what you get if you don't specify anything. So we're going to use that. The other property here is there's a migration property. I'll touch on this very briefly. It's a migration from unencrypted. This is something we've added recently. It lets you, let's say you've already got data in the database and you want to start encrypting a field. If you just slap the encrypted annotation on and you don't say anything about migration, when you try to read the object and decrypt that field, it's going to fail because you're trying to decrypt a field that isn't encrypted. What this annotation does is it lets you decrypt, or it lets you read either an encrypted or an unencrypted field value from the database, and then when you write the value back, it's always encrypted. The reason this isn't the default behavior is that authentication implies, or encryption implies authentication, right? So if you're able to successfully decrypt a field value, you know that whoever created that field value also had access to the encryption key. That may or may not be important for your use case, right? But for us, we're starting with all new data, so we'll just leave it just like this. I mentioned there's some configuration required here. Let's look at that. I have a little JUnit class set up. It's not really testing anything. It's just a convenient way to run a few methods. So let's take a look. There's I've got Couchbase running locally. There's some configuration here for those username, password, stuff like that. We're going to store all of the rabbits in a single document in Couchbase, and we're going to call it X is the name of the document. We're going to use a single encryption key. We're going to call it my key, and then we're going to configure the keyring. Let's look at this. We're creating a keyring. It's making kind of a fake keyring. So what it's doing is every time you run this program, it's creating a new random key, and then using this utility method keyring for a map to turn this map into a keyring. It's just a convenient way for testing things like this to make a keyring from a map. And then after the application quits, we forget about the key because we were just storing the key in memory. You can see the problem with this, of course. The next time we run the application, we won't be able to read the values that we encrypted because we forgot about the key. We'll fix that in the second part of the demo, but for now, we're just using this kind of fake keyring. Now that we have a keyring, we can use it. We can pass it to this simple crypto manager method. We'll see if it lives up to its name. And what this is going to do is return a crypto manager. So we're going to build and configure a crypto manager here and return it. What's this here? This is kind of a mouthful. This is the encryption algorithm that is included in the Couchbase encryption library. It is AES 256, CBC mode. It's authenticated. Takes a 64-byte key. This encryption algorithm, every Couchbase SDK includes with the encryption library for every language that we support implements this encryption algorithm. So it's portable across all the Couchbase SDKs of the different languages. So the key, we mentioned it takes a 64-byte key. Where does it get the key? From the keyring we just passed in here. So we're going to configure it to use that keyring, build it, and now we're going to make a crypto manager, and we're going to pass in, we're going to tell the crypto manager about the decryptor and the encryptor we want to use. This provider here acts as a factory for a decryptor and some encryptors. You can have, if you're using multiple algorithms, you can have one decryptor per algorithm, and then as many encryptors as you want. So let's say maybe you want to use different encryption keys in different regions. So we'll create a separate encryptor for region 2, encryptor for key, region 2 key. So like in the so now if we do this in our rabbit class, when we had the encrypted annotation, we could say encryptor equals region 2. But let's just use the default encryptor for today. We'll keep it simple. All right, and then we're configuring the encryptor to use the key, our my key. Now we've got a crypto manager. We're almost there. Now we just need to use this crypto manager when we connect to Couchbase. We start by creating a custom cluster environment right here and configuring it to use our crypto manager. Then when we connect to Couchbase, we pass in the custom environment when we make our cluster, when we connect to the cluster. The rest of this is standard stuff. We're just opening a bucket, waiting until it's ready, and then grabbing a reference to the default Couchbase collection that we're going to use to store the roster, or the Rolodex document. One thing to note, because we created a custom cluster environment, we are responsible for shutting it down when we're done. So after we disconnect from the cluster, we'll shut down the environment. That just cleans up red pools and other resources like that. That's all the configuration. Let's talk about what this demo is going to do. Here we go. We're going to upsert a document, a Rolodex document, and the content of the document will be a JSON representation of this list of rabbits. I really like working with the Couchbase SDK in this way, where I like to let it handle the data binding for me with the Jackson serializer. I like just upserting Java objects and then letting the JSON serializer, specifically the default Jackson serializer, handle the conversion of the Java object into JSON, and then vice versa when we read the document back out. So there's the command to create the document. I'm going to run it right now, and that'll take a while. In the meantime, so what's this display Rolodex? What else is it going to do? Oh, display Rolodex. It's going to do two things. First, it's going to show us display encrypted, which is just going to show us the content of the document as it is in Couchbase without any decryption. We're just going to get the document, the content as a Jackson JSON node, convert it to a pretty string. So we're just going to prettify a version of prettify the document and display that. So let's see, what does that print? That prints document in database. Flopsy, there's the encrypted magic word. Mopsy also encrypted magic word with that algorithm, and the my key. All right. So then the second thing we're doing here is then we're just that the display Rolodex does is after we display the encrypted version, now we're going to display the decrypted. So let's go there. And what's that doing? All right, this is fun. This is more cool Jackson data binding stuff in action here. We're getting that document, and then we're saying we want the content of the document as a list of rabbits. What's this type ref here? So if you're familiar with the Jackson type reference or a JSON type token, I think they call it, that's what this is. This is just a way to capture this generic type definition so that it doesn't get erased at runtime. So we asked for a list of rabbits, and then we're printing them out. What did we get? There we go. There's our rabbit name and magic word, the decrypted. And let's just verify here. I've got the Couchbase admin console over here. I'll refresh the page here. Refresh. There's the Rolodex document, and we can see that on the server, these values are encrypted. The encryption and the decryption happen completely on the client. The Couchbase server doesn't know what the keys are. So if the database is compromised, the encrypted values are safe. Let's see. Let's go back at IntelliJ, and that wraps up this portion of the demo. We'll come back in a moment and we'll see how we can improve the keyring situation to manage our keys differently. For now, let's talk briefly about how to add a custom algorithm. Now, I'm not suggesting, I gotta make this totally clear, I'm not suggesting you invent your own encryption algorithm. We all know that's a bad idea. But if you have a specific algorithm that you need to use that's not the default one provided by the encryption library, we'll show you how to extend the encryption framework to use your encryption code. So for this example, we're going to have a fake encryptor that doesn't do anything. It's just going to it's like a no-op. The plain text is the same as the ciphertext. Of course, this is obviously insecure. Don't do this. But this is an example of how you would implement the encryptor interface to make an encryptor for your own algorithm. So our fake encryptor, what does it do? So your encryptor can store arbitrary name-value pairs in an encryption result. An encryption result is basically a map of arbitrary property. The encryptor puts properties into the result, and then the decryptor pulls them out and then uses them to decrypt the message. This is important here. The fake algorithm, we're saying that the ALG field, the ALG field in the JSON should have a value of fake, so that when the crypto manager is asked to decrypt this value, the decryptor, here's the fake decryptor, because it was registered with an algorithm name of fake, it'll be the one that handles the decryption for that specific encrypted field. So the decryptor just reverses whatever your encryptor did. In this case, we're just getting the value we stuffed in the ciphertext, and we're returning it. So inside here, in your encrypt and decrypt methods, you can do whatever you want. You can make a call to a native library. You can make a call to a web service, which is how the Vault transit integration works. You can do whatever you want in there. Now that you've got your fake decryptor and encryptor, you register them with the crypto manager, just like before. If your encryption, if you wanted to use a keyring, you would pass it into the decryptor and the encryptor here when you create them to the constructor. But the fake one doesn't do that. So it's as simple as this. So you can adapt that however you want. Key rotation. This is the good stuff. So what is key rotation? Key rotation is when you have multiple versions of a key, and you periodically create a new version of a key and use that new version for all encryption operations. And then if you've got old versions of the key hanging around, you can still use them to decrypt fields that were encrypted with those old versions. But when you encrypt, you always encrypt using the newest, or the active version of the key. So why would you want to do that? If you think that a key has been compromised, you don't want to use it anymore. Another reason is that this limits the amount of data encrypted with a single key, prevents key exhaustion. If you are encrypting many documents, a lot of data, hundreds of terabytes of data, and an attacker gets access to all those ciphertexts. They can analyze all that massive amount of ciphertext. If you use the same key to encrypt this incredibly large number of messages, it's possible for an attacker to do analysis that might help them with an attack. So if you rotate your keys on a regular basis to limit the amount of data that's encrypted with the same key, generally a good thing for that reason. So how do you do it? The first thing you want to do is to make sure that this new version of the key is available to all of your application nodes. Because what you don't want to have happen is for one node to get the key and start encrypting new values with it, and then another node to try to decrypt it and say, hey, keyring, where's that key? And the keyring says, I don't know what this key you're talking about. And so you get a failure. So what you want to do to avoid that, distribute the new version to all your nodes first, wait for that to complete, then tell the nodes to start using the new version of the key for encryption. Step 3 is optional if you're doing this rotation because you suspect the old version of the key was compromised, and re-encrypt the existing data with the new version. I'm not going to cover that today, but I'll just give you an idea of how you might do that. You might use a nickel query because the key ID is encoded in the JSON. You can search for all the fields that are encoded with a certain version of the key. and then re-encrypt them. Waving my hands a bit there because we've got limited time today. But it's good to be prepared for that eventuality, so that you don't have to panic in the moment, right? How do you implement it? Here's one way. You can use a keyring with a convention for the key ID, where the key ID consists of the key name and the version with a delimiter in between. So the encryptor asks the keyring for the key by name. That's the base name without any version. The keyring says, you didn't ask for, there's no version here, you didn't ask for a specific version, so I'll give you the active version of the key. And then when it returns that key, it includes the fully qualified name with the key name and the version. The encryptor writes that fully qualified name into the JSON, and then when the decryptor decrypts it, it looks at that fully qualified key, hands it to the keyring, says, hey, keyring, give me this key. The keyring looks at it and says, that's a fully qualified name. You sure do know what you want. So it'll return that specific version of the key that the decryptor asked for. We need to look at a keyring in action. As I said, we'd fix up this rabbit Rolodex demo to do some key rotation. So instead of a keyring with a random key that we just throw away and forget, let's use file system rotating keyring. What's the idea here? In general, what we're going to do is we're going to store the keys on the file system. Kind of, why would you want me to do that? It sounds kind of crazy, but if you're in a Kubernetes environment, you might want your encryption keys to be Kubernetes secrets that you would mount into your pods via the file system. And then whenever your keys change, you can just push new updates of your secrets, you can refresh your secrets. So we're going to read these encryption keys from the file system, and we're going to follow a specific naming convention. So I'm going to look at this. This file system rotating keyring is a custom class. It's the code for this class is in the repository, or Java Rabbit Rolodex repository on GitHub. I'll show a link at the end of the presentation. And it has a few configuration options here. It has a path. That's the directory where it's going to look for the keys. There's a delimiter. This is what's going to go in between the keys, the base name and the version. File name extension, and a file name extension that indicates that this is the primary version of the key. And because it's doing file system operations, really quick, let's wrap it in a keyring caching and duration. How long do we want to cache the keys? Maybe how long? So this is how long can we wait for a change for a new change to a key to be reflected in the keyring? Maybe a minute. We can wait up to a minute. And how many keys do we want to cache? We don't. Lots, sure. And there we go. So now any request for a specific key is going to go through this caching decorator. And the decorator is, if it's not in the cache already, it's going to delegate to the file system rotating keyring to say, hey, give me this version of the key. And then it'll cache the value for a minute. And that's on a per key base. Right, so we've got a file system rotating keyring. These are the conventions. So let's create some keys on the file system. From over here, we're in this temp secrets directory. And we need to get some random bytes into a file. I'm going to use OpenSSL, rand 64 bytes out. My key is what we call their key, version 1 key, and we'll make the primary version of the key. And let's see, stump a key. Okay, those are our random bytes. And now we can run this demo again. We can upsert some more rabbits. So we're going to upsert some rabbits, and then we're going to emulate rotating the key. And first, let's look at this. Let's make sure this worked. There we go. And now the key. And you'll notice during this, we didn't change how we were configuring the encryptor. We're still the encryptor is still configured to ask for a key called my key. It's the key ring and says, oh, did you mean my key version 1? Here you go. So now let's rotate the key. We'll go back to the terminal. We'll create a new key. 2. And remember, we have to distribute this key to all of the nodes before we make it the primary, right? There's only one node here, but let's just go through the motions. There we go. Now let's bless it. We'll make it the primary. It's okay if there's temporarily 2 keys that are primary, as long as one of them is picked. Either one should be good. Oh wait, what's that? the primary. Oh, okay. Now all the nodes have the new oh no, we already did that. So now we're going to unbless the other one. So we're going to remove the primary thing from the first one. So I use Maven on A. And we'll just remove that primary prefix. So now what have we got? We've got two keys, or we've got two versions of this MyKey key. This version 2 here is marked as primary, so any new encryption is going to use that key. We'll go over here, and instead of upserting, which would replace the documents and encrypt everything again with MyKey 2, let's do something a little different. Let's do something fancy. Let's append a new rabbit to the existing document. We're going to leave the existing rabbits alone and just append a new rabbit, and it should be encrypted with the version 2 of the key, because that's now the primary version. So let's look. What have we got in the database? Flopsy still is MyKey 1. Mopsy, MyKey 1. Fluffy, the new rabbit we just added, MyKey 2. And when we decrypted the Rolodex here, you notice that we were still able to decrypt all of the magic words because those all of the keys are still in the keyring. That is the end of the rotating keyring demo. All right, we'll go back to the slide, and then we'll wrap up by very briefly talking about HashiCorp Vault. They have a transit secret engine. It provides encryption as a service. Basically, your encryption keys never leave the Vault server. And when you want to decrypt something, you make an HTTP request with your ciphertext, and Vault does the decryption and hands you the plain text, and then the same for encryption. So how does it work? We in the Java Couchbase field level encryption library to talk to Vault, we rely on the Spring Vault library. And so this first stuff up here, the Vault endpoint and the Vault template, this is standard Spring Vault stuff. Vault supports a number of different authentication methods. The Spring Vault library handles all that authentication stuff for you. You just have to configure that. And then you create a new Spring Vault transit provider and use that to make your decryptor and your encryptor. And this has a whole bunch of advantages. Spring Vault is, HashiCorp Vault has great support for hardware security modules and some pretty hardcore encryption policies. So you might want to take a look at that. That wraps it up for today. If you have any questions after today, please join us on the Couchbase forums. We love talking about encryption. And if you want to look at any of the code that we played with today, that's on GitHub too. Couchbase Labs /Java Rabbit Rolodex. All that's left is for me to say thank you. So thank you for joining me on this whirlwind tour of the Couchbase field level encryption library. We'll talk to you later. Bye.